For question number 2, my strategy is, so we're given this polynomial. For Roman numeral part 1, I'm just going to use the remainder theorem. The whole point of that is to predict what remainder you get upon doing a division. Roman numeral part 2, use the factor theorem. The whole point of the factor theorem is to show that something's a factor of something. And I think for Roman numeral part 3, I'm probably going to factorize it, because that's what I do when I solve a quadratic equation being equal to 0. Well, it's one of the methods, one of the 3 methods. So it could work for a cubic as well. So anyway, here's question number 2. So to find the remainder when you divide this by this, so in other words you predict what would be down here if you did it fully, you ask what makes that 0 and you substitute it for x in here. So the remainder is -2 makes this 0. So that's -24. I think that's -36. Yep, that's the answer to that. Roman numeral part 2, show that x minus 1 is a factor of that. So in other words, if we did x minus 1 there, we get a remainder of 0 there. In other words, that is something times something, and whatever the something is would appear up there. Okay, so how do you do that? Again, you ask what makes this 0, which is a 1. And you put it where x is, substitute that for x. So 1 minus 4 plus 5 minus 2, that's certainly equal to 0. So the answer is yes, because this being a factor of that is the same as saying when you divide this by that, you successfully divide it. It's like doing 1001 divided by 13. There's no remainder, you just get 17. Now, continuing that logic, so that was Roman numeral part 1, that was Roman numeral part 2, Roman numeral part 3. If you divide this by this and get that, it means that this is that times that. So in other words, the dividend is equal to the divisor times the quotient. So that means that this is equal to that times something. The something is what would happen there if you did this divided by this. It's pretty clear from the expansion that that's going to have to be a plus 2, because otherwise you couldn't get a -2 there. That times that is going to give you this. That times that is going to give you this. But I don't know how to find out what that is other than doing a full-blown division. So here's the full-blown division. By the way, remember my strategy here. My strategy is to solve this equation being equal to 0 by transforming it into a factorized form, because that's what works for quadratics and there's no reason to think it won't work for cubics. So that divided by that, x squared. That times that, x cubed. That times that, -x squared. Subtract, that minus that is blank. That minus that is -3x squared. Bring this down. Do that divided by that, -3x. And in fact, that's all I need there. I've now done that. But anyway, I'll just check. That times that, -3x squared. That times that, plus 3x. That take away that blank. That take away that 2x. Take away that. That divided by that 2. That times that 2x. That times that, -2. Subtract, you get 0, just like I said we would. So it was that equals 0, now it's this equals 0. Factorise that some more. And therefore the solutions are x equals 1 or x equals 1 or x equals 2. So in other words, x equals 1 or x equals 2. Now in fact, it didn't say, oh no, it did say hence. You can't just guess these. If Roman numeral part 3 had just said solve the equation fx equals 0, you could have just been lucky and guessed random numbers. Not completely random, make sure they're factors of this. So the only ones to choose from are 1, 2, -1 and -2. That's not that many to choose from, so that would have been a good strategy. But it said not just solve the equation, but hence solve the equation, therefore you had to use factorization because in Roman numeral part 2 you had demonstrated a factorization.